Hello. So this is going to be video number 2 of this section. Um, I think this is one of the most fun things we've done so far. Writing this up was extremely fun. We're going to look at a bunch of different types of linear transformations in the plane R2. And so remember, any point in R2 we can just sort of associate with a vector of length 2 just by flipping the point around. And so what this allows us to do is look at a bunch of different types of ways we can sort of shift points around in R2 and different types of transformations that we can do using matrices, right? Because the big punchline of the first lecture was that every linear transformation is also a matrix. And so there are a bunch of different types of linear transformations which you'll kind of have to trust me are linear. I'm maybe leaving out some of the details there. But it turns out that these transformations are actually linear. So one thing that turns out to be a linear transformation is the action of taking each point and reflecting it around the x-axis. So specifically taking each point xy and sending it to the point x negative y. Right? And so because this is a linear transformation, there should be a matrix which, so if I take my matrix A and multiply it by the vector xy, gives me the point x negative y. And, maybe you can sort of eyeball what's going on here and figure out the matrix, but part of the reason I want to give this example and sort of include this is to show how powerful that last theorem we introduced was, in that if we know where the point 1, 0 and the point 0, 1 goes, we can find this matrix A. So it turns out, again, all we need to do is know what happens to the point 1, 0 and what happens to the point 0, 1. Because, remember, A is going to equal T of E1, T of E2, or here T is the transformation, which we'll say reflects. So we'll say this is our transformation T, is reflecting each point around the x-axis. And as we learned, if we know what happens to the two standard basis vectors in R2, we know A. Well, okay, if I'm reflecting around the x-axis, the point 1, 0 stays fixed, right? So notice in specific, T of E1 is just equal to 1, 0, right? If I'm reflecting around the x-axis, the point 1, 0 doesn't go anywhere. The point 0, 1, however, notice we'll go to the point 0, negative 1. And so T of E2 is equal to 0, negative 1. And so combining these two facts together, our matrix A should be 1, 0, 0, negative 1. And sure enough, if I multiply this matrix by any point xy, I can verify that I do in fact get the reflected point I was hoping for. So at this point, I will say there are way more types of matrices like this than I have time to lecture on. I think it would be like an hour-long lecture if we derived each matrix like this. What I've done, and I want everyone to take a few moments to read this over after I'm done with this, because I have one more example which I really do want to talk about. I've attached an attachment. I've added a document that contains a lot more of these matrices and exactly what they're doing. a lot of these types of matrices can also be found in your book. The book uses like a picture of a fish. I did it as a square happy face, which I think I named Mr. Smiles. You can see the adventures of Mr. Smiles getting reflected and rotated and contracted and expanded by all these matrices. And so you can kind of see like what types of transformations are possible and the matrices that go along with them. And so I would encourage all of you to look at that, convince yourself why those matrices are in fact doing the types of transformations that they claim to be doing. And it's for a lot of reasons like this. You can actually look at what's going on with each of the standard basis vectors and kind of convince yourself why that's going on. So I want to do one more example here in R2. This time I want to do a rotation. So I'll draw out what's going on here. So I want to be able to take a point xy, and if you imagine, I can't draw a straight line. If you imagine a straight line going from xy to the origin, and just imagine that's straight. I want to be able to rotate this point an angle of, say, phi. So that's going to be my angle, and I want to rotate it to some point where the length of this line is the same. I'm just, imagine rotating it around like the circle of radius, of this radius by this angle. Right? So I want to take each point and rotate it. There's a good picture, well, I guess I shouldn't be talking about my art in that light. I'm not an artist by any means. But there's a picture that might be more descriptive than this of what's happening in that added document. But so I want to take each point, keeping the length of this line the same, I want to rotate it at an angle of phi. So t is the transformation. Which rotates each point a total of phi radians. And so we want to find the matrix for t. And so to do so, we need to know what happens to t of E1 and t of E2. So let's look at t of E1 and E2 on the plane. So I'm going to start with the point 1, 0, right, which is the point E1, right? So 1, 0, the length of this line is equal to 1. And when we rotate it a total of phi degrees, so let's say this is phi, what we get is we get a point here whose radius is 1, and the angle formed between the x-axis and this line is equal to phi. So recalling our trigonometry, we actually know that this point is the point cosine of phi, sine of phi. Right? Because this is rotating around the unit circle. And remember, if this angle is equal to phi, the x-coordinate and y-coordinates of this point are given by cosine of phi and sine of phi. And so t of E1 is equal to the vector cosine phi, sine phi. I'm going to run out of room for t of E2 here, so I'll move it a little bit. But we're actually going to find t of E2 very much in the same way. So now, if I look at the point E2, that's right here. So this point here is E2. This is getting rotated by phi degrees this way. And so this would be the point that 0, 1 gets sent to after rotating at a total of phi degrees. And so notice this point is just 90 degrees circulated from this point. So if I start here and add 90 degrees, I get to here. And so remembering our trig, that means that this point, well, here if I'm adding 90 degrees, that means the x-coordinate of this point is going to be negative sine of phi. And the y-coordinate is going to be cosine of phi. And so I know T of E1, T of E2. So the standard matrix for this transformation, well, is first column is equal to T of E1, second column is equal to T of E2. And what this matrix does, so this matrix rotates each point by an angle of phi, and this goes for any point I could pick. So any point I pick in the plane, if I want to rotate it, I just think of it as a vector, right, whose first entry is x, second entry is y, multiply it by this matrix, and that gives me the point that is rotated a total of phi degrees. And so I think this example really proves how powerful that last theorem that we introduced was, because, you know, while maybe the reflection matrix was a little more easy to just kind of look at and find, to me, in no way was this obvious. And in no way is it obvious that, like, a matrix or matrix multiplication should be able to do this type of rotation, like, around an angle. But by that theorem, knowing what happens to just these 2 points, you know, I can multiply A by any vector or a point in the plane and get this corresponding rotation, right? So if I multiplied A times this vector xy, I would get this point. And so, like I said, there are many more of these. Look at the added sort of document I've attached to under this lecture or somewhere in the week 2 things to do to see all of these different types of matrices. And I'll see you for lecture number 3 of this section.